Greetings Gen Chem students. This is a video introduction to your lab number 7 calorimetry, and it's a streamlined online version of that lab. And we're going to be doing calorimetry, which means we're going to be measuring the heat associated with various processes. What kinds of processes? Well, like a chemical system undergoing a chemical reaction, or taking a solid ionic compound and dissolving it into water to create a solution. We're going to use the science of calorimetry to determine the heat energy exchange between the system and the surroundings. And what is calorimetry? Well, calorimetry is the science of determining the heat of a system as it undergoes a process. But more specifically, calorimetry is determining the heat, Q, the heat energy exchange between a system and the surroundings as it undergoes a process based upon the measurement of the temperature change of that system that occurs as a result of the process. Now, we can use calorimetry. It works because of the most simple relationship that we observe in nature, and that is the relationship that everyone's aware of just through common experience. As you heat something up, as heat flows in, what happens to the temperature of that thing? Whether it's a piece of chalk or cheese or a chemical system, the temperature goes up. And as you cool something, as heat energy leaves the system, the temperature decreases. So we have this very simple relationship that says the heat energy exchange between a system and the surroundings is proportional to the temperature change of the system. And that's what we use in calorimetry. And the equations that we're going to be using in the lab this week are these on the board, and these are also in the protocol. The protocol is posted on D2L. And first of all, Q. We know that Q is proportional to delta T. And as we learned in our online class lectures, Q is also equal to the amount of heat energy exchange between a system and surroundings is exactly equal to the change in the enthalpy of the system. And what is enthalpy? Remember H, enthalpy is a system property. Just like every piece of matter has a mass, has a density, has a temperature, has a volume, every piece of matter, including you, has a very unique, specific amount of enthalpy. And as a system undergoes a process, a chemical reaction, heating, cooling, crushing, whatever it might be, that enthalpy is likely to change. And it just so happens that the change in enthalpy is exactly equal to the magnitude of heat energy exchange between the system and the surroundings. Right? So another equation that we're going to use, and this equation is in your protocol. Equation 3 is as well. Q is proportional to delta T, and we can get rid of that proportionality sign by introducing the constants of proportionality, and that's what equation 3 does. Equation 3 says that Q, the heat energy exchange between a system and the surroundings, the heat energy given up or absorbed by a system, is equal to the mass of the system times the specific heat capacity of a system times the magnitude of its temperature change that occurs as a result of the process it's undergoing. So that gives us a direct measure, a way of measuring the heat energy flow. We can measure the mass of the system, the specific heat capacity of a system is a constant, and we can easily measure temperature change. Equation 4 here is also in your protocol. We'll make use of that in part C of the lab. We're going to have a total of 4 YouTube videos. This will be the first one, the introduction, and then we'll have a separate YouTube video for each of the 3 parts of this lab, part A, part B, and part C. And we'll use equation 4 in part C. But what are we going to use as our calorimeter? To do calorimetry, you need a calorimeter, and a calorimeter is an instrument that allows us to measure temperature change. And we're going to use this calorimeter. Most calorimeters are very expensive and very accurate instruments, scientific instruments, but ours is neither of those. It's cheap and it's not terribly accurate, but it works well for a Gen Chem lab. It's going to be composed of 2 styrofoam cups, one nested inside of another, a styrofoam lid, and a thermometer that threads through the lid, and a glass stirring rod, which threads through the lid as well. And the lid fits on here, and that is our calorimeter. And what we're going to do in this exercise for all three parts, part A, B, and C, is we're going to introduce the system and the processes, the reactions that are going to occur inside the calorimeter. They're going to occur inside of this calorimeter, and we'll measure the temperature change, and from that we'll be able to determine Q, the heat energy. Oh, by the way, we're going to put the calorimeter into a 400 ml beaker so it just stays upright and doesn't get knocked over easily. Now back to our board here. It's important to recognize that the calorimeter is thermally isolated. The walls are made of polystyrene, which is a good insulator, and the system, our calorimeter, the system of our calorimeter is everything that is inside the calorimeter. And what is inside our calorimeter? Well, water, because we add that. The styrofoam cup, the inside walls, and the glass stirrer, and the thermometer, and the reaction system, the thing that for which we're measuring the heat flow. Those things are what make up the system, and they're all inside of the calorimeter. Now, the heat energy exchange, as the process occurs, as the reaction occurs, let's say we mix the components of an exothermic reaction in here. As the reaction occurs, it's going to give off heat energy if it's exothermic. That heat energy will be absorbed by the water, by the walls of the container, etc. But none of that heat gets out of the calorimeter because of the thermally insulated walls. So the total heat of the system is going to be equal to 0. Should have put this up here. Okay? Because all the heat is trapped inside. Nothing gets out. Now, there's going to be a lot of heat energy exchange between the reaction and the water and the inside surface of the cup and the stirrer bar and stirrer rod and the thermometer. However, we're going to assume, make a bold assumption here, that the amount of heat energy absorbed by the inside surface of the walls of the styrofoam cup and the thermometer and the glass stirring rod, that is indicated by cup, we're going to assume that that's essentially 0, or very, very tiny compared to the heat energy associated with the reaction and the water. And therefore, the heat of the system is going to be approximately equal to Q of the reaction plus Q of the water. We've eliminated that. And that sum has to be equal to 0 because all the heat energy is trapped inside. Nothing gets out. And now we can solve for what we're really interested in. We're running the calorimetry experiments to determine the heat of a process, the heat of a reaction, for example. So now we can use this equation to solve for Q of the reaction. And that would mean, since it's Q of the reaction plus Q of the water is 0, Q of the reaction is going to be equal to negative Q of the water. And look at this. Equation 3 gives us an equation to plug in for Q of the water. So Q of the reaction that takes place inside the calorimeter will simply be equal to negative the mass of the water that we put in there, the specific heat capacity of the water that's in there, which is a constant, times the measured temperature change that occurs inside the calorimeter. And that would give us what we're looking for, the heat of the system undergoing a particular process. And as I said before, you'll do that for 3 different kinds of reactions: a chemical reaction, a physical reaction, and a second kind of physical reaction that will allow us to determine the specific heat capacity of a metal. And we're going to have 3 other little YouTube videos that will describe the steps. I'll show you the steps in using the calorimeter, how the experiments is set up, generate the data. You'll have the data from those YouTube videos, and then you'll use the equations. There's our working equation. This is our working equation to solve for Q. And that's the story.